technology, and I thought population is just pretty straightforward to start with. That if we have more people, quite frankly, there's a smaller amount of capital per worker. I mean, that's just really easy in terms of thinking about, KPW is K over L. The bottom of our fraction gets bigger, the solved result gets smaller. And, so that was pretty straightforward, pretty easy. The second one's a little bit more tricky because we kind of always assumed up to this point that more technology leads to growth. And I think that's okay and a good assumption, except that, we kind of made an assumption about that more technology up to this point. We always assumed that society was getting and utilizing that technology to the highest or most efficient level. And what did we show in here yesterday? That may not always be true. And if society doesn't all garner the new technology, people end up not wanting the old technology. And that old technology wastes away, which effectively is like depreciation. It'd be like if we just burned our old technology at that point because you don't care, you don't want to use it, which resulted in effectively a lower KPW value. In fact, actually, we kind of even saw that yesterday in terms of a mathematical approach. I don't remember who was our calculating. You guys doing it somewhere? Oh no, you guys were doing it, right? Okay, so you guys were doing it, and at one point you each had a piece of paper and a pen. So our KPW was 2 per person, right? Effectively, when we got the new technology, you had a calculator. You didn't use your old stuff. You said, I don't use my old stuff. So we had one piece of capital, your calculator, Safa, that was effectively split between 2 people at that point. Yeah, sure enough, a lower KPW value. So that's kind of what we took into account yesterday. But we want to kind of rectify that with, what we've always talked about. This idea of, more people can make more stuff. And more technology should allow for more production. Solow doesn't disagree with that. He just says something else in society has to change. If you have more people and you want production to grow, like we've shown, you have to save more. And if society gets more technology and you want output to grow, like we've shown before, you have to save more. Effectively, in either scenario, you have to increase savings to allow either the new population to get capital or allow your existing population to all get the best technologically advanced capital. Effectively, Solow called this break-even investment. Break-even investment, BEI, the accounting abbreviation, because you will see this in accounting, and depending on how the finance program, how you kind of meander through it, it's very likely you'd see it in finance as well as a calculatable or determinable variable. It is determined a little bit different, of course, in accounting and finance, so we want to think about it in terms of economics. So let me give you the definition. Break-even investment is the amount of investment needed to keep capital constant when accounting for technological or population growth. The amount of investment needed to keep capital constant when accounting for technological or population growth. Effectively, in either one of these scenarios last class, our graph, it looked like this, where I had some d plus n plus g k function And after increasing either technology or population, I had a new one. Right, if I put my original savings function in here, I have my original KSS value. And we see that the effect of increasing either N or G or both, well, caused our KPW to fall. Less capital per worker would mean less output, but Solow said this is what would happen unless our break-even investment definition kind of comes to fruition. We don't want KSS2. We want KSS1. This is the value we want in society. Well, it is obtainable, just not at our current measure of savings. If we want KSS1, we know that there is a mathematical combination where KSS1 appears at our new higher rate of depreciation, taking into account N and G. Well, it would be this point right there. The distance between these 2 points is our break-even investment amount. So remember, we don't do a lot with this axis over here. We said, oh, it's kind of like the dollar value of output for each of these different variable inputs. But there is a dollar value that we could attach to it, right? This is some amount of investment 1, because it's some amount that we're saving in terms of a dollar amount. I'm just going to call it dollar I1. This is some amount up here that we need to save in order to cover the extra depreciation. This I2. BEI is equal to I2 minus I1, or this distance. So how could we see savings at that distance? How could we see that I2? Well, effectively, if we had some new savings function that showed SFK2, society would be able to afford all the same amount of capital that they had before any changes. I don't think this is stretching it too far. It's just different than how we always thought. We always assumed, because I mean, think back all the way back to one of the first things you did in 1900 was probably the production possibility curve, right? Production possibility frontier. We always just made the assumption. More technology, more output. More population meant more workers, more output. I don't think that assumption was bad at the time. We're just now giving it the caveat that more population also means society has to spend more on inputs. If they don't, you wouldn't get more output. We always assumed that they did. We just assumed it away effectively in that world of ceteris paribus, held everything else constant, right? Same thing with technology. We assumed society actually bought the technology. Well, technology's expensive. Your laptop was a lot more than your notebook. Yeah, that's what Solow was showing. That's all this model is. It's taking that common sense assumption and putting it into a modelable variable. That population, this is kind of like an overall summary, so maybe a good sentence to write. Let's see, if I'm going to do a good sentence to write, I better make it sound good. That population and technological progress lead to more output only if society is willing to save enough to equip its workers with the best available capital. Yeah, that sounds good. That's all Solow was saying, is that by themselves, population and technology don't actually guarantee more production. The only way it leads to more production is if society is actually willing to invest in that new technology or invest in buying their new workers' capital. If society is not willing to do that, it wouldn't lead to growth. That's all he's saying. And again, I think for most of us, that's kind of common sense, right? That was kind of an assumption we made in the PPF. No one in my 1900 classes ever raised their hand and go, wait, more people, how do we know society's buying them all tools? We just kind of assumed they were. Solow's just putting a variable to that assumption. We kind of assume they are. Now we know how much they have to spend and how it affects our model. Okay, so that's kind of our good little breakdown of break-even investment. Any questions on that? Okay, then I have a question, but it's going to take a little while to ask it. I'm going to have to do a board clear, so anyone need anything? Okay, so it's going to take a little while to ask it because I actually have to, well, I have to graph my question first. So I'm going to do this graph kind of big because I'm going to put a lot on it. If you want to wait and either do it at the end and only put what you need on it, that's fine. Or if you want to do it as we go, I'd make it big too then. So here's my question. Where should I put the steady state? Where? Now I know you're thinking like, well, wait a minute, you don't have all the information to answer that. Because steady state is where the SFK line comes in there. And I haven't put that on there, so I can't tell you where the steady state is. That's true, but that's not what I'm asking. I'm saying, where should I put it? Where should I draw SFK? For society? Actually, that's a different question entirely because in theory, isn't it possible that every single point on that decay function could be a steady state? Right? In theory, right, we always have one steady state that we kind of start with. You know, I always draw it and make it, here it is, here's SFK, and that's at some percent, right? 10% savings rate. And that gave us this point on the decay function was where our steady state was. But it doesn't have to be there because there could be other savings rates too, right? Like in theory, what if society was only saving 9%? Oh, well then there would be a different savings function at 9%. And if that was the case, well this would be our steady state. That's another point on the decay function. And what if savings was like, 11% or 13% or 12% or 16% or 18.5% or any possible theoretical number I could come up with, right? I would have all of these other possible points. So in essence, every single point on this decay function could be a steady state if I had savings functions that were going through. Those could all be steady states. Every point on the decay function could be one. So again, now we ask the question, where should I put the steady state? Which savings rate should I choose? this is actually kind of important in terms of really, I guess, planning policy, which is kind of the goal of being able to create this model. We want to be able to plan policy. Different values of savings lead to different steady states. So how do we know which one is best? So Solow reminds us of something, that each one of these savings functions is really showing us two things. It's showing us how much society is saving and how much society is spending. Right? Because if this initial one at 10% is savings of 10%, we know that consumption is 90%. So we have kind of simultaneously obtained information without even knowing it, I guess. So where should we pick? Solow answers that question with what is called the golden rule. The golden rule of the Solow model: society should pick the steady state value of capital that maximizes consumption. Society should pick the steady state value of capital that maximizes consumption. By itself, the definition means nothing right now. I understand that. It's fine. We'll kind of build to it. Let's kind of go back a little. To our very first day of Solow, we made some assumptions. Right? Remember, one of our assumptions was that y was equal to c plus I. We said we're going to work just in that parameter only. Y is equal to c plus I. Well, I can rewrite this. I can say, if I subtract like I from each side, effectively I can say that c is equal to y minus I. We know that at the steady state, that I, which we said is found from SFK, is equal to dk. We also had built a graph, and in our initial assumptions, we said that y was equal to fk as a function. Right? This was this graph from earlier, right? That's where that came from. But again, we've used that transformation a couple times. We used it in our math proof. We used it when we set up our whole model. So this is kind of now what we want to think about. I guess kind of calling it like a transitive property here, right? I can start plugging and playing things. Or I can just kind of rearrange all of this into this equation. C is equal to Fk minus dk. I mean, or you could say, you could call that SFK if you wanted, and which we'll kind of think about. But I want to kind of think about it in terms of this function. Now, the reason I want to think about it in terms of that function is I'm going to kind of go back over here to this graph. I've got all these colors on it. We have something else that is on this graph that, remember, we said we're not using for now. We know that y still exists on this graph somewhere. Right? Somewhere above all of this, way up here. Remember, we only zoomed in to the bottom, but somewhere way up here, is that y equals fk function. Which means that at every single steady state, we can determine consumption. Because at each and every steady state, I kind of wish I wouldn't have done these little green ones, sorry. It's okay. At every single steady state, we have a value for investment and a value for consumption. Right? That look, you should say, we kind of did this already, right? You're right. We did this in our very, very, very first graph. The only thing is we never had a steady state. Well, now we do. We know that all of these, in theory, could be steady states. And if this one was our steady state, well, that would make this distance I, and this distance C. And if this was our steady state, well, this distance would be I, and this distance would be C. But we know that at every single point, we can find the amount of investment and the amount of consumption. Okay, so here's all I want to do. And again, you don't have to do this if you can already see it. I just want to erase all my SFKs. Okay, so I'm going to do that. I'm going to be kind of careful. And again, don't mess with your graph. You can do another one again in a second. I'm going to do another one again in a second too. But I'm just going to erase all of these values and show what I'm left with. I'm left with this. What we see here is a picture of this equation. That C is equal to whatever my output function is minus whatever my depreciation function is, assuming we're at a steady state. Because we know that this point is where we separate out our I. Right? Good? Not good? Anyone? Then I'm going to erase this, rewrite it a little neater, so it's something that we can work with, okay? Still going to make it a little big, just, again, so we can kind of see these areas. So I'm going to redo that graph. So now I'm going to have a graph that, well, man, this is showing all kinds of things. KPW, right? We changed this to ding before, but now I also am going to include Y. I don't know, you could just make the word dingy if you want. I don't care. That'll work. That's equally as dumb as ding, so I think that'll be helpful to remember. I'm going to put my Y function on there. My output function, which we know looks like this. We've plotted output curves. We've plotted those Cobb-Douglas amounts. You made that chart on one of your homeworks. There's one of the study guides, 8-ish maybe, that says, hey, make a whole bunch more of these charts, right? So we know how to plot output. So Y is our function of capital. I think I've done them all lowercase, so I'll stick with that. I'm going to put my DK function on here. So here's DK. I hope I made that look like a straight line. Sometimes it's hard when you draw the curvy one first. I still want to caution us. Whose notebook can I steal real quick? You're not writing right now. Good. I'm going to steal yours. I'm going to go back to the very first day of solo. Hopefully you wrote it in yours. Maybe you didn't have that. And on the very first day of solo, oh, look at this. You did. We had a Y and a DK intersection, and I said circle it. It means nothing, right? Everyone remember that? Guess what? It still means nothing. The most common mistake people make on this golden rule is you say, that's got to be something. But nope, still on the first day, that rule still applies. It still means nothing. I'm glad you actually wrote that. You're somewhere in there. Ish. Right? So this means nothing. What did that last graph just show us? Before we had all the savings functions on and we started erasing them. It showed us that at every level of k that we could have, the distance between the depreciation function vertically and the output function was consumption. That's what that last graph showed us, the one that I said you can erase, you can do whatever, you can just leave or wait till I put this on. Because if this is if we're at the steady state, this will be true. Please note it is a vertical, that one's not super vertical, so it is a vertical transformation. So the golden rule said what? It said we pick the savings rate that maximizes consumption. So if the distance between the dk and the y function is consumption, man, I can eliminate a lot right away. Like, you know what, I can eliminate this. Well, that's clearly not the biggest c. And I could probably eliminate that, that's clearly not, and probably this, and probably this and this, and I don't know, man, the biggest c is going to be somewhere in here, right? How do we find it? All right, so we have to go back to math. Effectively, what are we looking for? We're looking for the greatest area between the two functions. I have a linear function and a curved function, which means mathematically we can solve for the area under a curved function using calculus, and that kind of sucks. Or we can go back to one of the precepts of what were you really doing in the calculus. I don't know if they actually explain what you really do in calculus. That would not have been my experience in calculus. It was like, hey, here's a bunch of numbers and formulas, make them do stuff. But we didn't know why. You know what you were actually doing? You were actually saying, what if we put tangent points all along this function and measured the distance between the two? Actually, that's what you were doing. Again, they don't actually explain that. I don't know if it helps explaining it, though. I don't know. That's what I want to do. I want to find which tangent point is furthest away. Tangent to what? Well, if I have a linear function and a nonlinear function, the greatest distance between the two is when a parallel line to my linear function is exactly tangent. So if I said, okay, this is my linear function. Let's use somebody's quiz here. This is my linear function. I want a parallel line, so I'm just going to shift it up and say, here's a parallel line right in here. Sort of. Hard to do. Right? That's a parallel line. Where is it exactly tangent? So where is it touching the curved function at only one exact little tiny spot? It looks like mine is right about there. At that tangent spot, L, sure. At that spot, my consumption is the largest. At whatever that KSS value is, that is our golden rule one. And in order to make it a KSS, what would we have to have? We would have to have savings coming through our dk function right there. You know what? I can add that in. I can just draw savings in there. Oh, no, I can't. Evidently, I missed it. There we go. We have our golden rule level of savings. We have our golden rule level of capital. Okay, we'll touch on it again a little bit on Monday, just to give it a, kind of like, okay, what did that mean? What did we do? Because I know we spent the time building the graph. So we'll touch again a little on Monday about it. Then we're going to go into the rest of chapter 6 and move on past that. Yeah.